All right, welcome everyone to today's event. So this is a joint event between heidelberg.ai and Freiburg.ai. And actually the story behind it is that we organized a NeurIPS meetup together back in December. And back then, during the planning phase, the guys from Freiburg.ai actually discovered Lena's talk, which she gave at a NeurIPS workshop, and we wanted to include her into a program. But unfortunately, her talk was on Saturday, so that was not possible. But we decided that we definitely have to catch up on this, and so here we are today. And yeah, I guess many of you know Lena. It's kind of a Heimspiel because she's from DKFZ and a dear colleague of mine. So it's my pleasure to introduce her today. So Lena, she did her PhD at the DKFZ and KIT in Karlsruhe and did a postdoc at Imperial College London. And now she's a professor at DKFZ, where she's heading the Division of Computer-Assisted Medical Interventions. And she's also a fellow of MICCAI and of ALICE, and she holds a ERC research grant. And so recently, Lena caused quite a stir in the MICCAI community with her work that's on how to properly evaluate and validate machine learning algorithms in biomedical applications. And as you can imagine, this is a very sensitive topic for many researchers. And I'm not sure if Lena knew back then what kind of hornet's nest she was going to poke into. I remember I first got aware of it during Annika's presentation at MICCAI 18, so Annika's Lena's student. And I remember after this presentation, that was the main discussion topic for the rest of the conference. I think the paper got 2 strong accepts and 2 strong rejects, so this shows how ambiguous the feedback was. And as I said, a very sensitive topic, but this resulted in that Lena is now heading a challenge board at MICCAI, where they work on standardizing all the biomedical challenges and improving the quality of challenges and the reproducibility and so on and so forth. I think we're gonna hear a lot about this now. So without further ado, please welcome Lena Maier-Hein.
Yeah, thanks, Paul. Thanks for having me. And I think I will start right with the presentation. So yeah, I actually started this whole challenge research after organizing basically my first challenge myself. And I remember this was in MICCAI 2015. And we basically organized this endoscopic vision challenge for the community to meet, etc. And then this guy appeared, who we had never actually seen before, and he gave his short pitch presentation for one of the challenges. And as you see there, he already said, okay, he already won a few MICCAI challenges, and that was scary. He also won one of ours, and this was when we started basically asking ourselves, do we really need domain knowledge still to solve problems in biomedical image analysis with machine learning? And now, a few years later, I would say yes, because I think there's a lot of things going wrong. Paul already hinted at it. I think the machine learning as it is traditionally seen is only the tip of the iceberg, and there's a lot to say about all the other components. To give you an example, I remember my professor, I actually studied in Karlsruhe, Professor Weibel, always saying there's no data like more data. That is true, of course, but in medicine it comes with some danger. And I was really glad about this recent paper here, which is about COVID-19 detection, basically, which shows how researchers just stack different data sets together. And this paper showed something very dangerous, which is that a lot of researchers basically merged a data set of infants with pneumonia with a data set of adult COVID patients. In other words, a classifier that can distinguish children from adults would get 100% accuracy on this data set. And this is just one example of a confounder. This would be a different one, cables in an image, or also even the position in which you take an image. These would be confounders. So this is just an example of why it is so crucial to really know a little bit about the domain that you're working in. So yeah, like Paul mentioned, I'm from the German Cancer Research Center. Yeah, it's located in Heidelberg. You should come visit sometime, maybe during one of our famous bridge parties, which we do together, always in Chemik, which is also where Paul's lab is located. And yeah, unfortunately for now, we have to do Zoom. Yeah, my group is working in surgical data science. So to scare you a little bit, in a recent paper, death after surgery was basically identified as the third leading cause of death worldwide. Cause is a little bit wrong in this context. It's just counting the deaths. This is after stroke and heart disease. So I mean, surgical safety is really, really important, which is why we work on this topic. But this is not what I want to talk about today. But today I want to talk about this overarching topic, really, of mainly also of validation. So yeah, let's start with the data set. I already mentioned a confounder. Now I want to talk about a different context. So thanks at this point to my our clinical collaborators from the University of Heidelberg, the technical collaborators. I really enjoy working with the statisticians, and by the way, and of course, my team, the team that's been working on this data. So yeah, sorry about this bloody picture, but this is the view of a surgeon during surgery, and you would probably agree with me. And I mean, I'm trained on looking at these images, but these are really hard to interpret. And what you really want to see is, of course, the target.
I'm not seeing your screen.
You're not seeing the screen? Wait. So I've been talking all the time, and you haven't seen the screen. This is great.
I even told people we're not supposed to see anything yet because I thought that's your free speech intro.
Okay, let me reshare. Wait, wait. I will go in presenters mode here. Maybe that helps the story. Now?
Yes.
Yes?
Yeah.
You see the full screen?
Yes.
Okay, wait, then, so this is sad. Let's see what you missed. So, yeah, this was the COVID one, the cables in the images. As the confounders, it was the bridge party, of course, you have to see, important bit. Surgical data science, I only mentioned, and now this is what I want to talk about. Clinical collaborators, technical collaborators, and my team. Okay, so this is what we want to, well, this is what we do see now. This is what we want to see. And the traditional approach to this is augmented reality, but with augmented reality, you're not able to see all the things. You see this now, right? You see my screen?
Yes, we see your screen.
Okay, great. Because there's no green bar around it anymore for some reason. The traditional approach would be to fuse information you acquired before the intervention with the patient anatomy. But this has some problems. To show you one example, if you wanna make a decision on the blood flow, for example, because you do a transplantation of a tissue, then of course images that you took before surgery won't help you. And I mean, you can try it yourself. Try to interpret these images. Can you tell which of these kidneys is perfused? I'm sorry, I will not show study images all the time. I personally can't tell, although I'm trained interpreting these images, and here you see the results. So I would probably think that this image here is less perfused compared to this one here. But as you see, we basically obtain ground truth with a contrast agent. This is not the case. So what we work with are spectral images. So RGB images, so the video images that you interpret in minimally invasive surgery, they're basically inspired by the way humans perceive colors. So you probably know that we have receptors for red, green, and blue. So this is how cameras are built. They filter this light and then they emit it in a way that humans can interpret the data. But of course, as a computer scientist, you're not interested in what humans can perceive, you're interested in the information content, and this is what we're looking at. So we're working with multispectral, or with spectral imaging in general, here shown for surface imaging. So basically for each pixel, we actually get a spectrum, like a sequence of values corresponding to the different wavelengths of light. And here you see some spectra for different organs. And then of course, our mission is to classify tissue during surgery, specifically the pathologies, but also the different tissue types, for example, for context-aware surgery or surgical robotics. And yeah, this went all well. This is the mean median spectra that you would get for certain organs. And I'm very happy that the spectral imaging team really is careful at looking also at the raw data, because at some point we had the hypothesis that there was a change that happened in the period of image acquisition. And I think from just looking at this data, you cannot tell you. I mean, just looking at this data won't tell you there's something wrong. But then the team took a certain time and point, split the data, and we observed there was actually a difference in the spectra that we acquired. And we found out that there was basically a camera update that we were never informed about. And this camera update wasn't supposed to lead to any change, but it did. And why is this so dangerous now? We always have difficulty explaining this to the clinicians, because then they say, well, but it's not a problem because it's just real life that you get different cameras. That's true, but the problem is that if you have imbalances in the data set, so the extreme case being, you record all the organs with half of the organs with one camera, half of the organs with the other camera, then you have a confounder and you will get a more favorable results with your algorithm compared to when you don't have this confounder. So yeah, what do you do with such a situation? And now back to the fact that we're collaborating with a statistician. At least when you think, when you have a hypothesis that there might be a confounder, there's nice statistical methods to work with this. For example, mixed models. I will go into this a little bit more in detail later. But I don't have the updated results for the camera because this just happened recently. But here you see an example where we wanted to quantify basically the variance in our measurements, and we wanted to know whether the impact of the individual, the patient basically, or the organ is bigger. And luckily in this case, we had the clear result that the organ had the biggest effect on our measurements, which is what we basically desire. But I will come back to this later. So data interpretation, really important from my point of view, and looking at whether you may have confounders, I think is so crucial. Yeah, so please think about this when you do your research. Well, annotations is another topic, and I think it's very underestimated actually. I really like this paper from Leo Joskovic's group, who really systematically analyzed inter-observer variability. And you already see from these different colored lines that there's a huge variance in how observers annotate structures. And this is of course crucial. We showed, for example, that in challenges, the ranking can change when you basically change the observer, the expert who annotates the data. Also, labeling instructions are important, and I want to illustrate this with an example. Sorry, again, some bloody pictures, but what we wanted to do was to basically delineate surgical instruments, segment surgical instruments. And you would probably say, well, this is obvious, right? It's just the artificial equipment on the organs, so it's easy to do. But then if you look at the details, it becomes tricky. So for example, in the case of occlusion, what do? Do you look at the foreground instrument like we do here? Yeah, that could be a choice. But then what do you do in the case of transparent objects? Do you then still not segment the instrument in the background, although you see it? Or take a text overlay. I think in this case, yeah, it kind of doesn't make sense to segment the text with the instrument, but then if you have another kind of text, like in this case here, it's absolutely not feasible to cut it out, right? So I think in the details, there's a lot of design decisions that you need to take, and a lot of them also require prior knowledge, like here in the case of the liver segmentation. So you may know that the vena cava is a large vessel that actually partially is inside the liver, but then it goes out. So then how do you segment it? How do you segment, is it included in this specific image that I'm showing you, or should you not include it? So it's this structure right here. So I think this clarifies that annotation protocols would be quite helpful to account for such ambiguities. Yeah, next topic, metrics. Yeah, somebody actually read our paper and brought up this story, which I kind of like. It's called the Cobra Effect. So you have it with snakes and with rats, but the story here from Vietnam is that there was a rat plague, and people would basically get a monetary award for handing in rat tails. And it was hoped that this way you can get rid of rats, but in reality, what happened was that people started just cutting off the tails so that the rats could reproduce, and then basically they could get more money. And this is obviously bad. And I think it's a good example of how a metric fails to measure what you actually want to measure. So to go into a bit more detail, again, a lot of people from DKFZ side involved. Actually, I should update this because now Paul and Fabian and Klaus are also involved here. The bias consortium, and yeah, more colleagues. I really have to update the slide for the new developments. So this is the DSC. So for those of you who work with image processing, you certainly know it. Sorry, this is a bug here. So it was used according to our analysis. We analyzed 500 competitions. It was used by more than 400 of them. And it basically measures overlap between the reference contour here, blue, and the prediction of an algorithm, orange, and gives you a value between 0, no overlap, and 1. So it makes sense, I think, at first sight, but you really have to look at the corner cases and also what you actually want to measure. So this is an example where you have a very small structure. This can occur if you want to, detect lesions in the brain, for example, and you see that a single pixel difference has a large effect on the metric. I mean, remember, it's between 0 and 1, so 0.5 to 0.8 is a radical change. And then if you remember the graphics on the inter-rater variability, then it becomes absurd to some extent. This was this image. Then, of course, I mean, you probably know that there's more and more work also on the non-determinism of AI. I mean, we're all aware of the random seeds and such aspects in the networks, but also there's not so obvious effects like the order in which computations are performed on the GPU, and all of this can lead also to very different predictions for the exact same architecture and the exact same data that you're using. Another problem is that, and Paul is actually one of those really being annoyed about this, but obviously the DSC is not a good detection metric, and you see this in this example quite well, I think. So there's 3 tumors, for example, or structures that you want to detect, and the prediction 1 has a much higher score than prediction 2, although it fails to detect 2 of the lesions. So from a clinical perspective, this is a disaster, but it's not captured in the technical metric that is always used. Yeah, now it's not only the, say, clinical perspective that always matters, it's also mathematical aspects that need to be considered. So again, an example here. This is basically an undersegmentation and an oversegmentation of a structure, and you see the dissimilarity coefficient is different. Now you can think about whether you want this, but I think awareness about such effects is quite important. So I talked about the red initially. Now I want to give you a concrete example of a challenge in which having the DSC caused a problem. So one thing that you need to decide is what you do when you include images with no structures, because then you can have a division by 0 when you use a DSC. So this is on the side of the organizers. So in this particular challenge, the organizers decided then to say you get a DSC of 1. Now, what does a clever participant do? Well, you could say, okay, if I have very few pixels in an image, in a challenge test image, then, because then I have small structures. Yeah, you remember that image of how single pixel difference affect the DSC for small structures. So the likelihood of getting a really cool score is pretty low anyway. So then maybe you should run the risk of setting them all to 0, because then the gain is quite high, because you could get a DSC of 1 if you're right. And that's exactly what this participant did. And that improved performance. And again, it's not at all what you want, because actually with this approach, if you do this with an algorithm, you get rid of potentially true positives. And that's clinically pretty relevant. The same happens in classification. I'm not going to go on for this forever, but just to show you some examples. I mean, a quite well-known phenomenon is imbalance. So if you look at prediction 2 would always basically classify the dominant class, can get really high scores. But I liked this recent paper that I found. It just came out by Hicks et al. And they analyzed a few aspects with respect to classification. And they found, for example, this study where an unspecified AI system was introduced to detect polyps. And basically the main result of the paper was a sensitivity of 99.7%, which is amazing. I mean, it sounds like a game changer. But then this group basically analyzed the data, all the available data that they found, and they inferred that actually the precision was 0.33, so it's quite low. And yeah, I guess it's a problem in this case that this was not reported. And yeah, the community is annoyed by this. We found this in a questionnaire already 3 years ago. They want best practice recommendations, and this is why we joined forces. So it's the MICA Society, the BIAS Consortium, and the MONAI, and we're currently working also with Paul in a prominent role, by the way, on best practice recommendations using a Delphi process. Hopefully the first paper will be released this summer. Yeah, our work actually started with this. I put this not so prominent because I've shown this already a few times, but just for those of you who haven't seen it, well, as you know, challenges are the way to benchmark AI algorithms. There's a lot of fame that comes with it, prize money, etc. So we asked ourselves at some point, and this was a starting point back in 2015, is the winner actually the best? And this was performed with a large group of partners. You see the logos here, and of course, they're all listed in the publication. I will not be comprehensive now. I just want to show you one slide on this because I think this slide illustrates the phenomenon quite well. So this is a challenge that is very popular. It's highly cited. It happens quite frequently. And you see the real world data. Basically, we had access to all the raw data. Now, when you rank algorithms, you have to make several decisions, right? So the obvious one is the metric. We already discussed that aspect. Then the not so obvious one is the ranking scheme. So for example, you can decide, and this is not commonly done, you can decide to first aggregate all the metric values and then rank. One problem being, what do you do with nonce? Because you cannot sum them up. Or, and this is one option to overcome this problem, you can first computer rank per test case, per test image, and then aggregate the ranks. And then you have to decide how you aggregate. I mean, for example, with the mean or the median or whatever quantity you want to use. So a lot of design decisions, and we showed, and this is not just a cherry-picked example, it's just one popular example. We see this all the time, that the ranks can be very sensitive to such changes. So this also included, if we left out test images, in one case we made the poorest performing algorithm the winner of the challenge by leaving out a single test case. We also played around with the observers, so there's a lot of factors that really influence the ranking. Of course, specifically when the data size is not so high. The size is low. Well, you know what I mean. Yeah, so what we did here was we recently released a toolkit, and I think, I mean, it's a first version. We're happy for feedback. I'm sure it can be improved, but I think it could be quite valuable, not only for challenges, but also for, you know, personal validation, ablation studies. The problem that we're addressing is basically uncertainties. So, you know, if your algorithm was A1, you would probably prefer the raw data on the left side. You see the box plots of the raw metric values, because in fact, on the right-hand side, we generated artificially the box plots from the exact same distribution. So there's no difference in performance. But these basically lead to the same ranking scheme. And we found that, what was the exact number? But I think it was more than 1/3 of challenges restrict their release results only to ranking tables, nothing else. And basically there's no advanced analysis schemes in general. So here in this case, for example, you can work with bootstrapping, where you put some noise in the evaluation process, and you see that in the first case, the algorithm is just the clear winner. It always wins. That's what this big blob, the red one here means. And whereas there's much uncertainty basically for the other ranking. Yeah, and this leads me to the general topic of challenge analysis, because I think here we are really in our infancies. And for this, I have to show you bloody pictures again, but this is how I can best explain what I'm concerned about. So, you know, we organized this challenge here, instance segmentation, and then the question is, what have we actually learned about the problem after conducting the challenge? I mean, what we typically get is a ranking schemes. So we basically know something like the distribution of results, but what do we learn about the problem? What do we learn about what is working and what isn't working? And now we're trying to find methods to address these aspects. This is a paper that is not yet on arXiv. It will be uploaded soon, but the general idea is to basically take the challenge data and then based on the qualitative results that you have, based on what you see or what is also maybe written down in literature, you generate hypotheses of factors that might influence algorithm performance. So in our case, for example, we speculated that overexposure could be a problem, too bright here. And then you do a statistical analysis to find the most impactful sources of error. And note that this is different to showing qualitative results because of all the biases that we're also subject to, such as, for example, confirmation bias. So this is a statistical method that just gives you relative to each other the importance of effects. it's a really hard topic, so I don't want to spend ages on it, and I'm not the expert to do this actually. So I'm very grateful for the collaborators. But to give you an intuition, what's going on. So you basically describe the output, which is, for example, the metric value or the aggregated metric value over the best performing teams or over all teams, whatever you want. You describe this as a function of image characteristics. So for a moment, let's get rid of the green part. Let's assume we only have the blue part. This would be the effects, the metadata annotation represented by binary variables. Now, what is tricky here is that typically you don't have clean data in a way that, say, you have images of the same hospital, and it's a very homogeneous data set. But what we observe instead in our field is a lot things like correlation between the test images. For example, frames extracted from the same video or images extracted from the same hospital. So when you do this in medication analysis, for example, typically you want to have the effect of different medications. That would be the fixed effect. But for example, you have other effects, or say a specific surgical procedure, but you have, for example, also the hospital, where maybe there's a hospital that has a particular good surgeon operating. So this means that you have essentially a hierarchy in your data. So it's not, you cannot see it as flat data, but you have some kind of hierarchy how you acquire the data. And this is when you need the random effects to compensate for such effects. So you don't really want to quantify them, but you want to statistically incorporate them to clarify that there's some correlation between variables. Yeah, we will release that paper soon to clarify the details. But for example, what you get basically is then something like this. You get, you can quantify the effects that you have. And then we found, for example, that underexposure was a huge factor, same occlusion of instrument, but interestingly, and this was to my personal surprise, overexposure was actually beneficial. I mean, now that I know it, I can explain it. The instrument is very bright. This can be basically used as feature, but I hadn't expected it actually. Yeah, so this is the say destructive view. So what is not working? The other view is what is working or why is it working? And I really like this image, which probably needs some explanation. So what you see is that's actually Paul is actually a co-author of this. So what you see is the algorithms competing in a challenge ranked from 1 to 100, and you see several architecture descriptions along with this. So for example, you see that both the winner and place number 100 used a unit. And I think there's a misconception in the community that it's all about the architecture, and this basically a certain algorithm wins because of a certain architecture. I mean, of course, there can be problems where this is the case, but in general, my point is that I think that the important aspects are often not reported. And I think this is a good example for this, and now we're working hopefully with a interesting insight to reveal such factors that really make a team win, basically. More on this in a year. Yeah, machine learning, last part. So I want to talk a little bit of the remaining time of some of our actual research, but again, you will see that also here the domain knowledge is crucial. Key contributors here, also people from my team, but our collaborators at IWR here in Heidelberg. And yeah, I already mentioned spectral imaging. one of the things that we're doing with spectral imaging is to recover spatially resolved certain tissue parameters such as oxygenation. This is an inverse problem. You see, basically, if I change the oxygenation in the tissue, you see that the measurement changes. But now we want to go the other way around. We get the spectrum and we want to recover the oxygenation. And now we have a hen and egg problem, basically, because we don't have an imaging method to give us spatially resolve the oxygenation, because if we did, we wouldn't do the research in the first place. So how can we then train the algorithm? So what we do, and I will not go into this at this point, is we basically leverage all our prior knowledge on how light interacts with tissue, on how tissue is composed, on how light interacts with cameras, etc., to generate simulated data. And just as the concept, as some context, I've shown this already quite a few times, but for those of you who haven't seen it, this is perfusion imaging, kidney. I showed you this example. So we built a multispectral camera to actually measure spectral data in real time. It looks pretty similar to a standard device with which you do surgery, minimally invasive surgery. And here you see that this was the very first patient that we measured. When we set the clamp to stop the blood perfusion, the estimated, in this case, it's blood volume, actually goes down from red to blue. And so blood volume is one parameter. Another parameter is the oxygenation. It's a different parameter physiologically. So here you see when we release the clamp, then the tissue is actually properly quickly reperfused. So this was the first part of the research, but then, and now is where the domain knowledge comes in. Now the hard part starts, because of course, when our industry saw these videos, they got interested, and they of course want to know whether our method is reliable. And now if you think about the problem and use your domain knowledge, you can come to the conclusion that there may be a problem, actually, because the problem may actually be ill-posed. So especially when we consider also the noise in the data, there may be radically different values of oxygenation that actually lead to the same or a very similar measurement. And this is, of course, not reflected in the point estimates. In this case, you would need to output either solution or the mean or something like that, which is obviously not the best solution. So we've been working a while on basically outputting full posteriors instead. So the method that we use is invertible neural networks. If you're not familiar with the concept, then I recommend the data science talk by Linton. It's online. I think it's great. It explains everything from scratch. Just for a brief overview, the architecture is based on these so-called coupling layers. I have to admit that for the first time I heard about these invertible networks, I was really puzzled, because for me, it didn't match neural networks and invertible. And it took me a while to understand that the key really is that in the backward and in the forward path, the actual networks, the S and T, are gone through in the same direction. So the whole coupling block represents an affine transformation, which is invertible. So you just basically for plus, you take minus, for multiplication, it's division. And then the whole function becomes more complex because of the S and T, but these don't need to be inverted. And that's really the key of this whole architecture. So you can go backwards and forward in this architecture. And then you can put such coupling layers together and generate complex functions. So again, I will not go into this in detail, but to give you an intuition in this specific context, so the measurement that we take is the Y, that's the spectrum. And what we're really interested in is the X, the physiological parameters. For example, the amount of oxygen in the tissue, the amount of water in the tissue, the temperature of the tissue. Now, the hypothesis is that Y may not capture everything that is contained in X. So we need to append Y with a latent variable that can capture the missing information. And we constrain Z to be Gaussian. And then, of course, because it's an invertible network, we have to append also X. We do this with zero padding. So these are the coupling layers. And to give you an intuition of how it looks like, when we get a spectrum, we continuously sample from latent space from our Gaussian. Each time we go through the network, each time we get an estimation for oxygenation. And because we do this so many times, we get a full posterior, basically. So this is where we started. And the first thing we did was, we actually worked with the spectral data that we had to investigate the benefit of certain cameras. So if you take this as a ground truth estimate, then an RGB standard camera would give you a quite wide posterior. And you can also see there's actually two modes in the data. And for this example here, a multispectral camera would actually give you a much narrower posterior. So we use basically this method for quantifying the performance of cameras. So this is where we started. But then, of course, we came across problems. So first problem is the zero padding. I mean, zeros are never or almost never great in such networks. This is one example of where it prevents things, for example, like maximum likelihood training. And also, and very importantly, the number of parameters directly depend on the input image size, right? So far, we only work with spectra, which are relatively low dimensional, meaning 16 to 100. But full images, it's a different story. So how to solve this? Get rid of the zero padding and use the Y actually as a conditioning. Then you're left basically with the Gaussian and the parameters that you're actually interested in the conditional network. I will give you an example in a second how this looks like, but that's not the end of the story, because if you would do it like this, then this would mean that the network would need to learn also the representation of your conditioning. And we want to go beyond the single spectrum Y, but towards full images, so it would be a bit much for the network. So you can actually pre-process your data with a conditioning network. So you learn a good representation of your measurements, basically, and then you use that as the conditioning. So let me show you two examples, and that will be the last part of my talk. One, I will show you for photoacoustic imaging, actually. So far, I talk mainly about multispectral imaging, which is what you see in the first row. Actually, here we see a phenomenon called spreading depolarization, which occurs when you have a stroke. And we also work with a quite novel technique called multispectral photoacoustic tomography, which also measures spectra, but tomographically. So how is this done? For those of you who haven't heard of it, consider this logo in a milk bath. Now, if you went to a gynecologist to do a 3D ultrasound, you would be able to see the sponge and the sign, but you would not be able to see what's written on the sign, actually. So now, if you illuminate the whole setup with laser light, then the photons will be absorbed, again, depending on the wavelength of the light and the tissue properties. That's important. Because of the absorption, there's an expansion because of the heating, and because of the expansion, the rapid expansion, actually an ultrasound signal is emitted. So light in, sound out. That's the technique, but I don't want to talk about it much more. But in this case, basically the image interpretation is a bit more complicated, and it's not so straightforward just to look at single pixels, because you need to basically account for the whole seen, which is why we started looking at CINNs, conditional invertible neural networks. So to give an example of what can be done here, you see it's actually a virtual scenery to be frank, and you see that in this specific pixel here, you actually get a multimodal posterior. So we are not certain about the value of oxygenation. There's two solutions that could actually yield the same measurement. Now, if we move the probe to a different pose, we can actually make the same problem solvable because we make the posterior unimodal. And that is something I find quite interesting for leveraging uncertainty, because we can optimize image acquisition by this. Here you see an animation of it where the probe is moved. It's a very simple setup, but I think it shows the message well enough. Final example is a different one here. We want to do classical augmented reality. So we take actually a single image during surgery, but we want to have the full 3D context that we have on preoperative data. So, I mean, you see the rotating X-ray image, but this is something you don't want to do because of radiation exposure for both the patient and the physician. So here, again, domain knowledge, we might come to the conclusion that especially when we're interested in the spine, the solution may actually not be unique because of the symmetry of the spine, right? And we show this by means of example. You see that two radically different poses of a patient actually lead to the same simulated projection image. So you actually have an ill-pose problem here. So we tackle this with CINNs. It's very early work. Basically first feasibility study, but the idea is to get multiple solutions via multiple modes. And here you see, for example, such a conditioning network such that you get an idea of it. So the invertible net is really just the different coupling layers. The conditioning net basically combines the information on the two images. I'm sure there's a lot of room for improvement in this conditioning network. It's just the first try. But already with this setup and a quite easy problem here, we were able to recover the multiple modes. And I mean, here you see an example of why this makes sense. So if you have an asymmetric spine, then you actually have a good solution. But if you have a symmetric spine, then there is actually ambiguity in the problem, and this can be recovered with the CINNs. Yeah, done, never done. But I just want to mention that what we talked about now is the ambiguity of the problem. And I think it shouldn't be mistaken with the out of distribution problem, because also in this case, even though the posterior suggests that we have a much better understanding of what's going on, if we see an example that the network never saw, it's just not trained to deal with it. So this is something that we're tackling separately, but I will not cover this today. It's also recorded from last CVPR workshop, and we use INNs to do so. Problem not solved, but interesting insights on that side. Yeah, take-home message. I believe that the reason that the expectations that people have for AI in medicine, specifically biomedical image analysis, are not met because we're doing the validation wrong. For all the reasons mentioned, we have confounders, we have wrong metrics, we have unstable rankings, we don't deal well enough with uncertainties, etc., etc. And I think we should keep on working on these problems and not only on the core machine learning. And of course, I think my team, because if it wasn't for them, I wouldn't be able to show anything. And thank you for your attention.
All right. Many thanks for this very interesting talk. I think your talk goes to show that you have to really put in a tremendous amount of effort in validating your own results, in looking not only twice, but multiple times. Is the metric, the accuracy we achieve actually representative of the problem we want to solve? And I really like the fact that at the second half of your talk, you sort of going from the sad part to the positive part, that there is ways, and if you put in effort, you can both validate your results and get new insights, develop new algorithms to actually bridge the gap from just optimizing on metrics to actually doing something that can at some point be used maybe in a hospital to help patients. So Lena kindly agreed to answer a few questions. I would suggest that you just use the raise hand button in Zoom. I hope I can see everyone's raise hand. So it's in the reaction on the bottom of your screen. You can use this raise hand button. In the meantime, maybe Paul, Jörg, do you have any questions for Lena? Anything?
Oh, we have there already a question from Brandon.
Sorry if I mispronounce your name. Brandon Malone, you have a question?
Sorry, now you should be able to unmute yourself, Brandon. It was locked before.
Okay, yes, thanks. Yeah, so first, Lena, thanks for the interesting talk. I think, yeah, that you raised a lot of interesting problems and challenges to address. But one thing I've noticed a lot is there are now a lot of papers that are coming out that are claiming that the machine learning algorithms have like better than human radiologists and other performance. So, I mean, do you think that these challenges that you mentioned are also applicable there? And you also, for someone who's say not maybe so familiar, how should we try to interpret those types of claims?
Yeah, so I think that's actually a big problem. So if you look at the papers, I mean, I don't know all of them, but I've looked at some of them. If you look at papers that claim superhuman performance or human performance, often what people did, they take all the data they have and then they split into train and test. And I think this is already a problem. One reason being the confounders that I mentioned, but also because in practice, this is not what you have. In practice, you want an algorithm to work in many hospitals. You will have a domain gap because the imaging devices are slightly different. You have a domain gap in surgery, for example, because different surgeons basically just use the hands differently. There's so many differences, and especially that domain gap problem, I think is a big one, and the confounders. So yes, I think that a lot of claims do not really hold from what I've seen. What can we do? I think we have to rethink the way that challenges are organized, for example, to start with the challenges. So what I would like to see is that in a challenge, we take the, say, top N, 5, 10, whatever, performing teams. And after the challenge, they undergo a real-life crash test. And then we can, systematically, for example, again, with the mixed effects models, see where they are strong, where they're not strong, and then we can tailor algorithm development to the gaps, basically.
I see. Okay, thank you.
Nice. Konstantin, you had a question?
Yes. Can you hear me?
Yeah, we can hear you.
Okay, great. Thanks a lot for the talk. When you discussed sort of the different metrics and challenges, have you also considered that some might actually ill-pose the problem a bit? So I'm thinking back to this example where you showed that the dice coefficient just doesn't capture this problem with multiple detections very well. And if I look at this, I mean, it seems like this is not really a foreground background segmentation problem only, but also like an instance segmentation or detection problem. And then there are very different metrics would be suitable. Exactly, yeah. So I think that in general, people don't put a lot of thoughts in metrics. So they just see, they look what is used a lot. They don't think about the corner cases enough. And then, for example, people use a segmentation metric for an actual detection problem. And it's interesting. So Paul and I discuss it so much because we're now trying to come up with best practice recommendations in a larger consortium. And we spend so much time, not even on the recommendations, but just defining, basically defining tasks for which we want to recommend metrics, basically finding similarities of problems that would justify a grouping by evaluation. And this would be such an example that you just raised. Did I answer your question, or? Yes, perfectly. Yeah, thanks.
Nice. Roland, you have a question?
Yeah, it seems, when you now identified a lot of confounders, the images you're working on, you don't know the metadata that actually you need to know. Is that right? So we have a big problem that the images we have, we don't know the metadata, like, for example, the spectra, that you identified as one of the confounders. So the question is, don't we have to specify the image metadata that needs to be, gathered? And for the already known, or for those images we already have, we have the big problem we don't know. So what you're doing is basically at the back end, try with statistics to find out all these things that are confounding stuff. Now that you know the confounders, is there any initiative that says, okay, if you take an image of a liver, if you take an image of whatever, then we need this and this metadata to at least be able to identify confounding stuff. Is that happening, or is that a suggestion, or is that something, because I mean, it's detrimental to not only machine learning, it's basically also detrimental to getting improvement in identifying what's in the image.
Totally, yeah, I fully agree with you. And I had a very depressing meeting today. I see Jan Zellner in the audience, he was there. So we have pretty cool data, we thought. And today we observed that basically we have a two-class problem, and we observed that the clinicians recorded all the images of one class in summer and all the others in winter. And now we really have a problem because this could be a confounder, because the spectra are sensitive to water, for example. I mean, what do we know about the water content in tissue in some of us? I mean, and this is something that we cannot compute retrospectively. So we came to the conclusion that we just have to redo the entire study, which is
yeah, this is very detrimental. So the question really is your group or somebody, I mean, this is now known in the community. Is there any effort to at least require, more of that metadata? I mean, we will not have the Holy Grail, but at least, some of the things, and the pressure to, submit papers and so on is on. And as you said, they just don't report some things. And if they not even measure, then even the reporting is not important anymore, because you don't get the comparability anyways.
Yeah, no, you're absolutely right. So this was our conclusion. Our conclusion was basically we identify all the confounders also with our expert knowledge, right? Because some of the, I mean, I've only mentioned a few, but we really have some that require quite some expertise. And then we make people aware of them. And then we really need, I think, specific for the different domains, like you say, protocols, how to acquire the data, including the metadata. And I mean, in medicine, it's already acknowledged, right? So you actually get a publication from registering a study protocol. That's an actual publication that is peer reviewed. And it makes sense because then people can say, well, we used the study protocol by XY et al.
Mm-hmm.
And I think the same, we should have something like this. We should have the same for annotation protocols. We should have, for acquisition protocols. And I think my personal perception is, I mean, some people are not aware and some people are just hiding. Because, I mean, for us, it was also a disaster because, so what we have is basically a Nature publication. And if we hadn't analyzed the data so thoroughly, I think nobody would have noticed. But we were so careful. Now we cannot just, I mean, we had an accuracy of, I don't know, 97% or something. It's basically a game changer for this case. But yeah, now we're not comfortable reporting, of course.
Yeah.
But I agree, yeah, it should, we need changes, but of course there's not a lot of incentives by people to do so, because then, I mean, already all the work that we're doing, we're trying to improve quality for, I didn't mention everything, but we also released guidelines for what you should report in a paper, and people feel really annoyed by us that we restrict them so much, their freedom. I mean, yeah.
But I think it's essential that from your community, because you're the expert, this has to come and within the community to pressure on that. And there's lots of from the European community. There's once in a while, these efforts to compare studies and compare the problems. And in my field, it's even worse because we don't have these clear things, even much more fuzzy stuff. And they, for example, found out that a lot of studies in the neuroscience and the influence on behavior, are basically just useless because they are not comparable, they are not, and then the European community finances a lot of these things. And in the end, you don't get something out. But they don't have a solution, But I mean, it seems to me that what you now did the effort is we have a possibility, at least with this metadata, to get a better analysis. And then we know probably more that what could be done with machine learning,
Yeah, I agree. And I think we really need the statisticians aboard.
Thank you very much. Great.
All right. I don't think I see more raised hands. Maybe one more question on my side. It's kind of similar to the two previous questions, but now, assuming you were overnight to become the head of the Kaggle community with the Kaggle challenges, what do you think would be like the first initiatives you would do to make these to make these challenges more closer to the real life?
Well, I always like asking such questions. Now I know how it feels from the other side. Yeah, it's a tricky question, but so I would get rid of the political things. I mean, of course, if this happened in practice, I would first familiarize myself very well. But yeah, I think I mean, the confounders is probably one of the things I would really look at. I mean, I showed this initially, but there's been Kaggle challenges organized based on the data that I showed, the pneumonia infants and the adults. So I think that's a good example. I mean, I can only speak for the biomedical field, but it shows that there's things going wrong, and I would just put more focus on quality. I mean, they have really nice things. They get a lot of attention and attract a lot of participants. So a lot of cool things going on with Kaggle, but yeah, more quality control from domain experts is probably what I would go for. And by the way, there was a question in the chat, which is very brief to answer. So for the hyperspectral imaging, the question was asked if special cameras are required. So yes, special cameras are required. So it depends a little bit on what you want. So there's always a light source and the camera. For example, we work with a standard light source, so we only change how we receive the light, and you can do this with several different techniques. If you also want to work in the near infrared light, for example, where you have important information, then you also need to exchange the light source compared to the standard equipment. But yes, it's not the standard camera that we can use.
Thanks for the clarification. We have one more question from Gendarme, maybe.
Yes, hello. Thank you very much for the very interesting and inspiring presentation. I did like it very much. Coming back to the discussion about the metric. So I mean, most of the people are using dice, as you mentioned, but do you have like something against it, or do you think that people should start exploring more at the start? You know, like is it like still the first that we should try when we are working on a new project, and then see if it's actually matching the expectations, or directly test, let's say, 2 or I don't know, like how would you try to solve that problem actually?
Yeah, so there's controversial discussions on it in the scope of our Delphi process. So if you take the technical perspective, I mean, DICE, the advantage of DICE is that it's very, very widely used. It makes your results to some extent interpretable and comparable. What I don't like about it is that it's an overlap measure only, so it doesn't respect contours at all. So I like complementing it with the contour-based metric, normalized surface DICE, for example. So I think you know, capturing the complementary information that is relevant is important. And then, of course, I mean, you should be aware of edge cases. If you have really small structures, I don't think the DICE makes a lot of sense, as I just showed you. The other perspective is the domain perspective. So you go only towards what you actually want to measure. So maybe from a clinical point of view, it's only important to know how many lesions you have in the brain. Mm-hmm. Then the perspective could be, so then just use the count as your metric, period. I think we will end up with something, yeah, more or less with both. So I think it makes sense to have for each family of problems something like a standard metrics that are reported because people are familiar with them. But when you do a ranking, for example, for a specific clinical problem, I would be in favor of measuring what is clinically relevant or in the respective domain.
Okay. Thank you.
All right. I think we have asked enough questions. We can release Lena, and thank you very much again. Paul, do you have any last words?
Yeah, well, thanks again to everyone. Lena, great talk, and yeah, see you around. Thanks to the Freiburg guys for co-organizing.
Thank you.
Yeah, to all the participants. Hope to see you at our next event, and have a good evening. Bye.
Bye.
Thank you. Bye.